Satellite imagery is transforming how we measure and understand global poverty. From miles above Earth, high-resolution photographs capture details of villages, farms, and cities that conventional surveys might have a hard time capturing. By analyzing these images with machine learning and artificial intelligence systems, researchers can identify patterns of economic inequality and develop more targeted anti-poverty programs. This post explores how the marriage of Earth observation, EO data, and causal inference techniques is helping build new insights into the geography of poverty, and why this matters for researchers and policymakers. Some limits of traditional poverty analysis. For decades, poverty mapping relied on household surveys, census data, and national statistics. While valuable, these methods have critical gaps. Cost and scalability. Surveying remote or conflict-affected regions is expensive and risky. Temporal lag. Data often reflect conditions years out of date. Spatial granularity. National averages mask hyperlocal disparities. Enter Earth observation. Satellites like Landsat and Sentinel provide free, global, near real-time imagery, capturing everything from crop health to nighttime light intensity. When combined with ML, this data becomes a proxy for socioeconomic conditions or a new view into causal processes, offering a complementary lens to traditional methods. Planetary causal inference. Based on these insights, our work and those of other researchers in planetary causal inference (PCI) demonstrate how EO data helps uncover drivers of poverty and evaluate the effectiveness of interventions. Here's how it works. Satellite images as proxies. ML models extract features from satellite imagery, like roof materials, road density, or agricultural patterns, that correlate with poverty. For example, tin roofs versus thatch can indicate economic status, while vegetation indices signal crop yields. Causal inference at scale. By analyzing how interventions, e.g., cash transfers, infrastructure projects, affect these proxies across space and time, researchers estimate conditional average treatment effects, CATEs. This answers questions like, does a Uganda anti-poverty program work better in areas with dense road networks? How does urban design in Peru modulate the impact of education grants? Case studies. In Uganda, EO data revealed that grants for youth entrepreneurs had stronger impacts in areas with pre-existing market access visible via road networks. In Peru, satellite-derived land use patterns helped identify villages where multifaceted anti-poverty programs were most effective. In Georgia, USA, pre-treatment, satellite sequences predicted which neighborhoods would respond best to water conservation campaigns, contributing to the geography of poverty. This work in PCI illustrates how EO-based AI systems don't just help map poverty, they can help redefine how we conceptualize it and the processes undergirding it. Here are some new possibilities opened up by this line of inquiry. Multi-scale understanding. Traditional poverty maps provide static snapshots, but poverty itself is dynamic, unfolding across multiple spatial and temporal scales. New multi-scale approaches, like multi-scale concatenation, transform single-scale causal models into powerful tools that capture both fine-grained individual heterogeneity and broader contextual dynamics. Modeling drivers. Causal EO-ML models detect non-intuitive patterns. For instance, nighttime light growth might correlate with economic activity, while deforestation rates could signal vulnerability to poverty shocks. From villages to planetary analysis, EO enables cross-scale analysis via transportability or generalization analysis, linking household-level outcomes to regional trends, e.g., how climate change amplifies poverty in dryland farms. Policy innovations. Here are some potential implications for policymakers. Targeted interventions. Instead of one-size-fits-all programs, governments can tailor aid using EO-derived CATEs. For example, we can model how different households will respond to an intervention based on features of local context, such as household, village, and farm type. Real-time monitoring. Satellite data can evaluate policy impacts mid-implementation. Did a new school improve local outcomes? EO proxies, e.g., nighttime lights, construction activity, offer some clues before surveys are conducted. Predictive analytics. ML models trained on historical EO data can forecast poverty risks, like predicting which regions are vulnerable to crop failures and trigger early interventions. Challenges and future directions. While promising, EO-driven policy analysis faces some limitations. Resolution versus privacy. High-resolution imagery risks infringing on privacy. Balancing granularity with ethics is critical. Model interpretability. Future work needs to further consider interpretable ML methods to provide further why behind causal insights from causal EO-ML methods. Integration with local data. EO proxies should complement, not replace, ground truthing and community input. Future research directions also stand out. Develop domain-specific foundation models fine-tuned on EO data for social science. Improve multimodal fusion, e.g., combining satellite images with mobile data or social media. Expand causal frameworks to account for spatial spillovers, e.g., how a program in one village affects neighbors. Conclusion. The integration of Earth observation and machine learning is a new tool in poverty analysis and, hopefully, alleviation. By transforming satellite pixels into policy insights, we gain a new ability to understand inequality's roots, and analyze interventions and possible solutions at scale.